Welcome back to my channel. So today we're going to continue on our earlier video, which was part 1 on the MNIST Dataset and getting an introduction to machine learning. And today we're going to continue with building our model and training it, and then taking a look at our accuracy and the results. And so if you haven't watched part 1 of this video series, I will put the link in the description below. That should be a good introduction, and sort of getting caught up in what we're doing in this code here. All right. So just a quick review, in case people forgot. Here we just imported our libraries. We tried to load the data set into these 4 variables. We then just took a look at these shapes, and then we plotted the first photo in each of the different classes to get a visual idea of what they look like. We then noticed that each of the values in this data set are quite large, going up to 255. So we reshaped it so that each of the values land between 0 and 1, which make it easier for our model to run, and it'll be more stable overall. And then lastly, we reshaped our data because our model only accepts 2-dimensional data. And earlier, as you noticed, our data was in 3 dimensions. And so we reshaped it to only be in 2 dimensions. And so now our next step is going to be building our actual model. So here we go. We're going to start off with defining our model, and it's going to be a Keras sequential model. And so in further videos, I'm going to explain what sequential and all the different models which I'm using here actually mean and what they do. And so essentially we're going to start with something called a dense layer. And it's going to have 128 neurons. And our input shape is going to be 784. And then we're going to use an activation of ReLU. And I know a lot of this might not make sense at the moment, but in my next video, I am going to explain what all of these different things mean. So essentially, we have our number of neurons here. We have our input shape, and then ReLU is sort of a mathematical function that takes the input and converts it into an output that you want. All right, and so then next up, we're just going to add another dense layer here. And we kind of want the neurons to decrease in powers of 2. So our next one is going to be 64. And then our activation is going to be sigmoid. This is just another sort of math function that once again takes the input and converts it into the output of the layer. All right, and then we're going to do it 2 more times, where this one is now going to be 32. Our activation is going to remain sigmoid. And then our last layer has to have a value of 10 because there are 10 different classes which we separate our images into. And then this one is going to have an activation of softmax. And once again, it's just a normal activation function, and I'll explain what these different activation functions mean. Okay, now lastly, we want to compile our model. We're going to use the Atom Optimizer, which is one of the most popular optimizers there is. Our loss is just going to be categorical cross entropy, and then we are just going to look at, for metrics, we're just going to look at the accuracy of the model. Okay, and so then just to get a good visual idea, we're just going to print the summary of this model. And when you take a look at that, you will see that we have 4 different layers, the output shape of the 4 different layers, and then the number of parameters that are going into each of the layers. All right. And so just like a quick introduction to these terms, because I know it's a lot going on at once, but essentially the Atom Optimizer just adapts to the learning rate of the model. The categorical cross entropy, it's a loss function that tries to improve the accuracy of the model when we're having multiple classes and we're trying to classify between multiple classes. So now we have to actually train the model, and that is done by a command called model.fit. And in model.fit, we are going to set the x value of the model.fit as our x train reshaped. And then we are going to set our y value to something called Keras utils to categorical y train, and then we're going to run it for 10 epochs. And so just a quick overview of what all of these terms mean. What the to categorical y train does is it converts the digits into something called one-hot encoded vectors, which turns everything into a 0 or a 1. And so it's essentially going to be an array of 10 zeros, 1 for each of the classes. And then if, let's say, it's a 1, that means our second 0 is going to turn into a 1, which tells the model that the model has predicted this value or this image as a 1. And then 10 epochs essentially just means that we're going through the data set 10 times in total. All right? And so then to actually take a look at how the model does and its accuracy, we run that, and this is going to take a couple seconds because it has to run through the model 10 times, right? And so what you're going to notice here is that the accuracy is going to start going up with each epoch that is run. And then hopefully your loss should be going down. So we can see that originally the accuracy was 78%. It's gone up to 96. Now it's at 97. Now it's going to hit 98.1. If we keep going, it hits 98.6. Now we're at 99%. Around 3 more epochs left. We're at 99.2%. All right, and now you can see that our highest has been, I think it's going to hit 99.5%-ish. Okay, so hit 99.6. So as you can see, a lot of these values are changing a lot. And so just to get a good evaluation, we're going to use model.evaluate. And what we're going to do is we're going to feed our test data into the model to see how it does. Because remember, we never fed our test data, we only fed our training data. So when we take a look at this, we were able to receive an accuracy of 97%, which looks pretty good to me. Okay. And so what we're going to do is we're going to take a look at some predictions here and trying to get an idea of how our model looks visually. So if we say that y pred is equals to models predict the reshaped test data, and then we need to get our labels out. When we take a look at this, it's going to predict on all the test data, and now we're going to plot a confusion matrix over here, where our labels is going to be equal to our y test, and our predictions is going to be equal to our y pred labels. And now we are going to plot a heat map using the Seaborn library, and you can take a look right here, that when we plot out this heat map, we see that, this is, so essentially we have our different classes over here and our classes over here. And so we can see that 965 times when the actual class was a 0, the model was able to predict it as a 0. And we can see that in a straight row going down, with the lighter the color being better. And so we can see that our model was able to predict 1 really well, with 2 being a close runner-up. But overall, we can see with the amount of blackness that isolates a straight line that our model has a pretty good accuracy, and it was able to predict these labels pretty well. All right, so that is going to be the end of part 2 of this video. I am going to make a part 3 which explains in depth everything I did, and then it's going to predict, using this model, a random test sample from the entire data set, to see how our model trains on unseen data. Okay. So if you guys like this video, please make sure to like, subscribe, and comment. And I will see you guys in part 3 of how to learn your first machine learning program. Thank you.